Welcome everyone. I'm Marcus. I'm full stack developer on Constellation. I'm here with Ryle. Can you present yourself, Ryle?
Hi, I'm Ryle Gohausen. I'm the director of protocol engineering. So today, we'll be talking about Metagraph dev core concepts and some Metagraph design patterns. Marcus, you want to kick it off?
Yes, sure. I will start with the dev core concepts, the initial part. Let's start. Cool. First, I will talk a little bit about the Metagraph layers concept. We have discussed it in the previous video of the Euclid that we have the concept of layers, and here we're going to dive a little bit more into this concept. In Metagraphs, we have three different layers. We have the Metagraph L0, the currency L1, and the data L1. A Metagraph doesn't need to have both L1 layers, but it must have at least one of the layers. So the currency L1 layer is used to send the currency transactions. Currency transactions is the normal transactions like we have with other blockchains, where we just select one value on destination wallet and some fees, and then we transfer that token amount. Here we have also the data L1 layer that we use to implement the data transactions. Various types of data can be sent to a Metagraph. For example, in Door Metagraph, we send the full traffic data from devices to the Metagraph. So let's break this down. The data L1 layer, we use this layer to send different types of data, not only currency transaction like we are mentioned, but we can send various types of data, like check-in for a device. We can send updates for any kind of Metagraph that you want. I don't know, like water spend, energy spend. We can send that types of data to the Metagraph. So we have this data L1 layer that will handle this kind of transactions. If we take a look at the image at the right, it kind of describes that the layer 1, we receive the transactions, the token transaction, and the custom data transactions. This layer 1 produces blocks, and these blocks are aggregated on the Metagraph L0. And on Metagraph L0, we produce the snapshots, the currency snapshots. Those snapshots are sent to the public networks, such as testnet, integration net, and mainnet. We call those networks as global layers. Is the HTTP networks, hypergraph. So discussing a little bit more about the difference on currency and data transactions. A currency transaction involves transferring L0 tokens from one user to another. These transactions don't require special handling. You only need to provide a destination amount and fee. Just like I've said, we can just select the destination wallet. Let's say that I want to send 100 tokens, 100 egg tokens, or 100 L0 tokens, your Metagraph token, to a different wallet. Let's say that I want to send to the Ryle. I will provide Ryle addresses, the amount that I want to transfer, and the fee, just like that. But in contrast, data transaction involves receiving a custom data types directly on your Metagraph. Handling data transactions requires addressing several key processes, such as like, what kind of data will send to my Metagraph? How this data can be validated? How can this data be stored on-chain? How can states be updated according to the new incoming data? So these are kind of questions that will be answered in the next slides. But when we are handling data transactions, we have a lot of questions to answer, like these ones. Cool. Let's go ahead and talk about this data application. The data application, or data API, is a module available in Currency Framework developers for ingesting and validating custom data types on the Metagraphs. It offers a set of tools for managing data interaction within the Metagraph, flexible enough to support a wide range of applications, such as IoTs, NFTs, or custom application-specific blockchains. So I've given an example previously that we are receiving check-ins on the Dora Metagraph. We can receive various types of data, and at this scenario that I've talked about the Dora Metagraph, we have real devices that count full traffic event, and then we send that data directly to the Metagraph, directly to the Dora Metagraph. So it's one IoT use case. So the primary function of the data application is to accept the data through a special endpoint on data L1 layer located at post data. So when you build your Metagraph or your data L1 Metagraph, one endpoint will be available. It's the /data endpoint. This endpoint it will be the endpoint responsible to receive the data and ingest this data to the Metagraph. So receiving a request triggers a series of lifecycle functions for the data update. So when we send a transaction, a lot of lifecycle functions will be triggered in a sequence, and this sequence starts like receiving the transaction, validating transaction, combining the transaction. I will explain in details the lifecycle functions in the next slides. But this process includes validations, consensus on data L1 and L0, and eventually the data inclusion into the custom data portion of the Metagraph snapshot. So just like the currency, the data will also produce data blocks, and those data blocks will be sent after consensus to the L0, and the L0 will reach the consensus again on the L0, and we will produce the snapshots to send to the global network. So we will have the blocks for currency, and we have the data blocks for data transactions. Okay, the concepts of states, lifecycle function, data flows that I've just mentioned, I will explain in the next slides. So let's start with the data types. To create the data layer, like to start using the data layer, we need to implement the following functions. I've left the functions here, just so we get familiarized with the functions. We have the Metagraph L0 and data L1. By default, this function is not implemented on the L1 and L0. You need to extend, override this function, and start implementing the lifecycle functions there. But on Metagraph L0, you need to override this base data application L0 service, and on the data L1, this base data application L1 service. These functions enable the data layer for you. So for each function, when you take a look, you're going to see that we need to provide three different data types. The data update, that a trait for the incoming update. Like let's say that I'm sending my real device's full traffic data. I've created an update to receive that data, like serialize, deserialize, encode, and everything related to that kind of data as my update. I also have the data on-chain state and the data calculated state. These two ones is related to the states. We have two different types of states, the on-chain and off-chain, and I will talk about the difference between the states, but you just need now to understand that we need to provide these three kinds of data. So each of these traits should be extended to create your own updates and state. So it's required to extend those data to create your custom updates, your custom states. So this is required to implement the lifecycle functions. Let's talk about the data flow, like the flow of data since we send the transaction until the end. So the data, it will be accepted to the /data endpoint. So this data is parsed and reformatted if necessary. Like we have a function called assign a data entity encoder. I will explain about this function the next, but this function will receive the request, the raw request, and then format the request to be in the pattern that Metagraph understands, the signed pattern, because we are expecting a signed message. We need to sign the message and then get this update, sign the update, and provide and transfer to the class that we are expecting on Metagraph. After parsing the data, if necessary, we're going to trigger the custom validations that run on data L1, the validate update. This is the first function that validates, and this validation will happen on the L1 layer. And we use this function more to schema validation. So let's say that I want to avoid a value to be lower than 0. So I can do the initial validation here and reject if this is my condition. Then the data is packaged into blocks, run through L1 consensus, and sent to L0. The data blocks are sent to L0. Then we have additional custom validations that we run on L0 called validate data. This is the second round of validations that happens on L0, but different than validate update, the second round happens with the state. So we have the state at this level. We can compare our incoming updates to the current state. So right here, I can compare my updates to see if I will not have duplications on the state. So let's say that I already have one update and I will reject this because it's a duplication. So I can validate here to reject my update. So data is packaged into on-chain, snapshot, and off-chain, calculated state representations on the combined function. I will talk about this state management in a bit, but this is two types of state that we have. So we have the state that will persist on-chain, and we have the state that should remain off chain. So this is two different types of states that I have. So the snapshots undergoes consensus and it's accepted on the chain. So after all this, we produce the blocks, the currency snapshot was produced as well. We send to the global zero. Once it's validated, this snapshot is merged on the global network, and we have this currency snapshot present on the global network as well. This is an image. I will start talking about the lifecycle flow that we have, but right here we have an image that try to illustrate the flow on the currency and on the data side. The currency one, it's way easier than the data one because we only have two options, the transaction validator and the serialized block. Only those functions that should be implemented on currency on one side. And the data one, we have more functions. We have the signed data entity decoder that I've mentioned earlier. Then we call the validate update. Then we have the custom serializers that I will also talk a bit, because we need to know how to serialize and deserialize my data, my update, my states. I need that information. Once I call this, we're gonna reach the Metagraph L0 block where we deserialize everything to, like, the serialization is getting that entity and transform to byte array. This deserialization is the reverse. We get the byte array and transfer to the classes. Then once I deserialize, I will call the validations. I will combine my new states. I will serialize the blocks again so they can go on snapshots. The consensus will be reached. We will send the snapshots. So this is just an image that you can take a look. All these functions will be detailed on the documents, on the Constellation docs. You can take a look individually to each function to understand what's the behavior, what this function does, what step this function is called during the process. So let's move forward. Let's start on the lifecycle functions with Genesis. In Metagraphs, similar to the global networks, we need to initialize the initial wallets and balances. On the currency layer, on the Metagraphs, on the global networks, we have the Genesis file where we provide the addresses and the initial balance of these addresses. So it will be the amount of tokens that your Metagraph will start. But unlikely the global networks, the data Metagraphs also requires the initialization of states. Right here we have states, not only the addresses and the balances, but right here we have also the states. So the on-chain and the calculated state need to be initialized. Those states are data structure that I will talk in a bit, but we need to initialize. So let's say that my calculated state is a map of the relations between addresses and values. I need to start this map empty or with initial values. Genesis function works like this. This function is implemented on the L0 layer, and we use this function to start our states. These states are set up during the Genesis lifecycle function, like I've mentioned, and is located on L0 layer. This function ensures that both states start correctly, providing a foundation for the Metagraph's operation. So right here, this function is called only when we start a Metagraph the first time as Genesis. We call this function, populate our states, and then we will start from there. The second round of lifecycle functions is the parse, serialize, and encoding, and as well the deserialize and decoders. We need the functions to parse, serialize, and encode the data. This data includes the Ryle request, updates, and states. Like I've mentioned earlier, to receive the Ryle request and parse them into the signed update type, we use this function called signed data entity decoder. By default, this function uses a source function, a source from Scala, called source entity decoder, that just transforms a simple JSON into the object. But right here, we can receive any kind of data at this endpoint. Let's say that I want to send a XML, a JSON, a route string, a number. I can do all these options since I get this update and transform to the signed update type. The output of this function is the signed update type. And this update is the custom update that you are implementing to your Metagraph. So you will decide what will be this type. If it's going to be only a map, if it's going to be a relation of fields. So this is your decision when you're implementing your Metagraph. We also have the encoders and decoders. As the name suggests, these functions handle encoding and decoding data type, particularly incoming updates. We have two functions to encode and decode the updates, called data encoder and data decoder. Like I've told, the description of this function and the functionality will be available on the Constellation docs. And the serializers and deserializers handles the serialization and deserialization of data. This process involves converting data to and from byte arrays. Just like I've mentioned earlier, we need to know how we will transform our current classes to byte arrays and vice versa. Like we need to also know how we're going to transform the byte array back to classes. This is the available functions. Some of available functions: serialize update, serialize state, deserialize state. We also have serialized calculated state, deserialized calculated state. So all serialized and deserialized will be available on the documentations. The second round is the validations. After we talk about the serialized and deserializers, we need to touch on these validations because it's really important. When we are receiving updates, we need to validate them to ensure that they are valid and consistent. Data metagraphs have two types of validation that operate in different layers. So this is one thing that metagraphs can do perfectly, is like validating your data. Let's say that I'm sending a specific kind of data. These validations will handle that incoming update to accept or reject the update according with your logic. So like I've mentioned earlier, let's say that I have a number field that I cannot accept lower than 0. I can put on my validations to reject all the updates lower than 0. Of course, this is a simple example, but we can expand this validation to a lot of examples. It's like it will be according to your use of case of the metagraph. The first type of validation operates on the L1 layer, and this function performs the initial validations, such as schema validation, just like I mentioned, validating numbers, validating if it's present, if it's not null, if we are providing correctly, then the fields that we are expecting, we can do these validations. Since it operates on the L1 layer, we don't have access to the state. So it's just initial validation that we don't need to rely on state to check if it's valid or not. The second type of validation occurs on the L0 layer. And unlike the validate update, this function have access to state. So we can do here validations that depends on the state. Let's say that I'm accepting a hash and I don't want to have duplications. This hash is my unique identifier. So if I receive a second update with the same hash, I can go on my state and see, do I have a hash like this? If yes, reject my updates. So I can do this validation and reject duplications at this level. Again, this is just a simple example, but you can extend comparisons to your state to see if it's valid or not. It will depend of your metagraph use case. The last portion is the state management. The data API encompasses two distinct types of states: the on-chain state and calculated state. Each of these states serves unique purposes. As the name describes, the on-chain state contains all the information that is intended to be permanently stored on blockchain. So the on-chain state will be the state that you want to persist on the blockchain. It will be the public state that it will be available on the blockchain. And the calculated state, this state exists off-chain and it's constructed based on incoming data, and it's not stored on the blockchain. So this calculated state, unlikely the on-chain state, will be the state that should remain off-chain, that will not be persisted on snapshot. And this state it's going to be built every time that you start a metagraph. This state will be built according with your updates. So we will receive the updates, the older updates, or we have calculated state checkpoints that I will mention in a bit, but we have the updates, and these updates will build the calculated state remaining off-chain. Each state described above represents functionality from the data API. To create these states, you need to implement custom traits providing the data API. I've mentioned earlier that we have 3 data types that we should implement: the data update, data on-chain state, and data calculated state. So right here, saying again, we need to extend the data on-chain state trait to implement our on-chain state, and the same for our calculated state. We need to extend the data calculated state. We have the lifecycle functions to handle the state management, such as combine function, set calculated state, get calculated state, and hash calculated state. So, as previously described, both states serves distinct purposes. The on-chain state is designed to persist information that users want to record on blockchain. This information can be public and will be available on the snapshots on the network. You should store data that you want to be on-chain in on-chain state. Calculated state is intended to hold data that should remain off the blockchain. For example, let's consider that your application needs to use a key for fetch from API, and only your Metagraph can decrypt and execute the request, and the response should not be public. This scenario is a good use of case for calculated state because you can store sensitive information. Again, this will depend for your Metagraph because we need the update to build the calculated state. So you need to be sure that you will not provide sensitive information on the update. And only Metagraph will handle this decrypt and calling external APIs and remaining the state off chain. So this is just a use case. Be sure to keep what you don't want, like sensitive information and that kind of data outside the on-chain state, and maybe the update, because the update is also public on the data blocks. This is just a use case. Second use case is because we have a 500 kilobytes limit size for snapshots on the network, currency snapshots. And let's say that you have a lot of updates or heavy updates, and you can't put that information on chain state because it will exceed the 500 kilobytes. If you exceed that number of kilobytes, your snapshot will be rejected. So that's another use case for a calculated state. You can put large informations on the calculated state because we don't have a limit there. The calculated state will be stored like by default in memory. We have examples in memory on the Metagraph examples. But the functions set calculated state, get calculated state, and hash calculated states allows you to implement your own storage for calculated state. You can store your calculated state in databases, SQL, NoSQL, so you can use the service that you prefer to handle calculated state. Updating the state, both states are updated based on the return value of the combine function. I've mentioned earlier we have this combine function. When we are handle the lifecycle functions, the combine function is the function that will get the update, compare to the state, merge to the state, and the output of the combined function will be the updated state on both layers, on chain state and calculated state. Not layers is the best word, but like the both states, on chain and calculated state. But this updates, it occurs in different times. Like the on-chain state update, it's updated immediately after a combined function during the snapshot building. Since the data should be included on snapshot, it must be updated before producing the snapshot, the artifact. So right after we call the combined function, we will update the on-chain state because this information should go on the artifact, the snapshot. So the snapshots go to the consensus, and after the consensus, this data will be the official data, and this data should be on snapshot. That's the reason that we call right after the combined function. The calculated state update is different because it's updated after reaching consensus. So after we reach the consensus of snapshots and we decided or a snapshot according to the majority and that stuff, this is going to be our official snapshot. After this, we call the functions to update the calculated state. The set calculated state function is called when we need to update this calculated state. And this function, like I mentioned earlier, is the function that you can customize the way that you prefer. You can implement the set calculated state function as you prefer. Examples including storing the calculated state in memory, but you are free to use any storage mechanism, such as databases, like I mentioned earlier. We have the Metagraph examples. It's probably on the documentation on the Hackathon website. You should see the examples. We store everything in memory, but feel free to use your storage mechanism. Before we move to this work in demos, I just want to mention, I've talked earlier that we have checkpoints from the calculated state. When we are handling metagraphs, we have a folder that we will store our snapshots, but we don't store only the snapshots in the files. We also store the calculated state. So this checkpoint is necessary. So when you start a metagraph again, you don't need to traverse the entire chain to build your state. So this checkpoint is like lives in the folder called calculated state over the data directory. And this folder contains by ordinal the calculated state at the current ordinal. So when we start your metagraph again, not Genesis, but the rollback, we will traverse and see if we have that ordinal present on calculated state. If yes, we will use this candidate and we will merge all the updates ahead of the last finding state. This is a little bit complex context. We will have next series demonstrating the Metagraph live code. On this live code, we should show the directories, the files, and everything, so it will be more clear. I know that there's a lot of information from this video, but on the live code, we will demonstrate about these directories where we can store this calculated state. And the last thing here, the Metagraph workers daemons. In Metagraphs, you can spin up workers that are triggered at intervals to perform various operations. These workers can call external APIs, send updates to the Metagraph, check consistency of your Metagraph. So you can perform any async operation on these workers. We call these workers /daemons because we have this daemons name that you probably see on the examples, but it works like workers that it triggers between intervals. The Constellation provides one example of using these workers to fetch from external APIs. The Alpaca Metagraph is the latest Metagraph released by Constellation at this present moment of this video. And on this Metagraph, we have a few workers that operate in both layers, L0 and L1, Metagraph L0 and data1. And these workers call external APIs, process the data, and send this data to the own Metagraph, ingest this data to the Metagraph to be updates. And when we receive this data, we process like a normal request on the /data endpoint. It's pretty straightforward, the implementation of daemons. We have support for this. So take a look at the Alpaca Metagraph example. You should see a lot of information there about these daemons. And I know that I've talked a lot. I know, Ryle, can you talk a little bit now about the core concepts?
Of course. Thank you, Marcus. That was fantastic. Okay. So we're going to be discussing briefly some high-level design patterns that you might be able to use when thinking about what to build in terms of an application. So we're just going to go briefly over and sort of explain what Constellation is and what metagraphs are, and sort of how they compare to conventional contracts and what might be the strengths and weaknesses, and sort of guide you into what applications you can develop and best practices for development. So, for those who are unfamiliar or, have gone through the docs but are still a little, confused, the best way to characterize the Metagraph framework is the blockchain in a box, which is a, sort of phrase that other people have coined in similar development aspects, where people come in and see conventional smart contracts and they can't fit their application into it, for whatever reason. This could be because it doesn't support light clients, it doesn't support libraries or dependencies that they need to pull in, or they don't want to rewrite some portion of their application in a contract language. There could be, dozens of different reasons why a blockchain framework is more appropriate. And for any of those developers, they're left with the question of, should I build an entire network from scratch, or use a framework? This framework is really targeted at people who want to customize and control the entire application stack for a custom blockchain. So we're gonna, throughout the series, you'll see how to deploy an entire network as opposed to deploying a contract. You'll be able to use regular programming code in order to write your application, use regular libraries and dependencies. It automatically connects to our existing network for interoperability. And it provides sort of a guide rail for blockchain development so that you don't have to worry about a lot of the underlying nuts and bolts. So, again, compared to a contract layer solution, this allows a lot of different capabilities and things that are very difficult to express with conventional contracts. So that's sort of the characterization in compared to other networks and other cryptocurrencies and other blockchains. So the biggest question is, what can you build? Again, the main strengths here are allowing you to pull in external dependencies and integrate with external resources. So rather than creating a series of different contracts that has to pull Oracle sources with externally managed sources, and dealing with multi-sig updates on oracles, or using Chainlink, or dealing with a very complicated integration, you build one microservice that essentially handles everything and is distributed to the number of nodes associated with whatever configuration you want in terms of scaling out the workload. So the ideal pattern here follows a service-oriented architecture where each one of these metagraphs represents an individual atomic locking service where they're producing blocks and snapshots corresponding to the data associated with your service. So again, it's trying to follow conventional design patterns where we're treating one metagraph per service, and that's sort of treated as a microservice. And I'll talk a little bit more about what the request response model is and how it translates from a conventional application to a blockchain application. We don't have as strong support for existing contract languages, although we are working on framework development toolkits to pull in EVM and compile EVM code so that you can do more interoperability and reuse existing contracts. So let's jump into the request response model. So again, the high-level analysis of this is that you're trying to build a microservice that operates a blockchain network that allows users and clients to issue some type of request, which Marcus has introduced as the data update. And that request has a corresponding transformation of state depending on the validation conditions, and that state yields the response. So let's look at Bitcoin or Ethereum in under this request response lens. A send transaction or a consume UTXO transaction would take some prior existing knowledge or state. It would have a user authenticated signed request, and it would yield some change in state to the chain data that yields the response. So basically, the request in this case would be a send transaction where you're trying to send some currency. The response is seen in there's this number of confirmations, and you provide this Merkle proof that shows that it's been accepted. So this request response model is what we're sort of trying to abstract in terms of the data updates. And when you're trying to design your application, you should think about it in terms of a service that's taking in requests, that's updating some sort of shared, distributed, validated state, and issuing responses not directly, but rather through the transformation of the chain state. So again, in this model, the clients would have to just subscribe essentially to the chain information to see or materialize the response. We allowed the construction of an addition of custom endpoints. So, if you need some sort of transformation there to, visualize to the user what the response to this data update is, it can be implemented through a custom transform of the chain state. And one of the biggest considerations here is, what do you consider a chain data request versus an additional request? So it's very important when designing an application to essentially segregate requests into whether or not they're going to be putting data on chain, or whether or not they're just a polling function used by somebody running a node to get information about things that have happened. So a data update is something that you want to put on chain that represents, something that is signed by the user and does some sort of transformation of the existing state data. If you're just interested in something like querying an address or getting a balance or something like that, it's not really the same type of request. It's more of something that you can put into a custom endpoint, and something you could store in a data store or store, access from the calculated state or anywhere else. You don't really want to store large response objects on chain. You want to store the minimal representation of the state. This could be, a key value map. It could be any other minimal representation of the change that is intended to go on chain. Additional information could be hydrated or enriched based on the chain data. So you could come up with a whole set of additional APIs that reference some pre-validated chain data with enriched information or transformed fields or anything else like that. So again, the comparison to a conventional service is there is a distributed and validated, response in the form of the state information that everyone agrees upon. And the request model has to be authenticated. So it's an authenticated request associated with some type of user or device signature. And it's very important to distinguish between chain data requests or, sort of auxiliary information. So again, what is a request? It's generally corresponds to something that requires a signature. This could be, a signature from a device like a truck or a car that is providing some sort of authenticated information. It represents a diff update, so it's not ideal to try and store a large update of the same repeat of data. So for instance, if you have a device that's sending out some series of updates, you wouldn't want to send the entire history of updates in every request. Each request should be just the diff in terms of changes. So just, the most recent piece of information should be sent. Similarly, if a user is making some kind of update request or something like that, you don't want to store the user's entire history. You don't want to store anything. You just want to store the incremental change that has happened. And that way, when the chain is built, it's built out of a series of diffs, which if you apply, you get the most, you get each version of the state at each point in time. So, again, avoid huge amounts of data. The more you can focus on metadata or hashes, the better you can use external integrations. You can use internal data stores. You can use lots of additional tools to sort of trim down the amount of data that's in each request. Because that data is going to be, sort of interoperable with other chains, and your internal Metagraph can do lots of other information and data store access internally that it doesn't expose to the wider world. So again, anything in the request should be associated with a change or a diff. As far as storing the response, again, very important, avoid huge amounts of data in the response. If your response is, serving an object, like you're implementing a block store or, a storage or Filecoin equivalent, you don't want to put the entire, client serving response into the state or calculated state. It would be unwieldy. So it's not, you really need to focus on putting metadata in the requests and the responses, and then allowing the validators to deal with much larger amounts of data internally, but not exposing it or communicating it. So if you're dealing with much larger amounts of data, you really need to be clever about the right way that you invoke your validator functions and what you store in the state. So again, this is something where you want to avoid like duplicating balance maps or duplicating maps over and over. You should be updating individual keys and values based on the diffs that are operating within each request. So again, when I say build response out of state, there are many different ways to build different types of responses. So basically, this state is going to be synchronized across all these machines. Within it, you could transform many different values out of it. If it was a balance map, you could have an endpoint that pulled one address as balance. If it was a energy usage map, you could have aggregate energy usage by state or by country or by device ID. There's many different ways to view what the desired response is out of an individual request.
And just interrupting you real quick, I forgot to mention, but Ryle is pointing correctly. We have another lifecycle function, so you can create your custom roads. like Ryle mentioned, you can create your own roads, your own get roads to retrieve information from your state. So as well, like I mentioned, it will be on the documentation, but just so you can know that we have a roads lifecycle function where we can implement the custom roads to retrieve information from state.
Yeah, that's perfect. And so again, this is the sort of the benefit of using a framework where you don't need to go into the hassle of building out the entire client library yourself. Implementing a REST API is extremely simple and straightforward. And you can just add existing routes to the routes that are already available and built into the framework. So the next thing we'll be discussing is one of the other major strengths of our framework is external integrations. So conventionally, if you've seen other smart contract platforms discuss light clients, this is typically how they're implemented through a platform level feature that allows a REST API call or something else. This is conventionally pretty tricky to support on most standard networks. It's generally expected that you're going to rely on an Oracle service, which has a lot of both security implications as well as integration headaches. One of the benefits here is using a single microservice that is able to both run your validation code and seamlessly offer external integrations. So in our examples, we have REST API calls and other external integrations examples, and you're able to pull in client libraries that are pre-existing code. So if there's some service that is essential to your application that has an SDK for it, let's say you want to pull in the SDK to pull the Bitcoin price from some exchange, you can simply pull in the SDK and use the existing client library without having to deal with the difficulty of setting up a custom Oracle, integrating with some Oracle solution. You can just use it as though you were writing a regular program yourself. So client libraries are very well supported, and all of this can be integrated into validation and chain state processing. The daemons that Marcus referenced earlier can periodically pull this so that you don't repeat the operation or repeat requests. And ideally, this should be held in an internal data store or at least an in-memory data store for proper resource management. One of the main considerations when using external integrations is reproducibility. This is also called, idempotency in REST API language, although reproducibility is the sort of more easy to understand term. But a repeated call with the same input should lead to the same result. This is to give you an example with price APIs, for instance. If you call Coinbase latest price API, just the standard one, you will get a result that is down to the millisecond, but it's not necessarily guaranteed to be consistent across different machines. So even though you're calling the same API, you're going to be getting different values that are very, very slightly different based on the millisecond that you get from a random response of getting the latest price. If you're dealing with an API that's like that, that's essentially non-reproducible, you're going to have to make certain adjustments to either use moving averages or trailing numbers, or otherwise quantize or discretize it. It's much, much better if you can find an API or implement a wrapper service in front of an API that's going to yield a reproducible response. So an example of this is some Exchange APIs, and I'm using Exchange APIs because it's a very, very common use in crypto, but you could substitute this with any other API. It could be a weather API or anything else like that. Ideally, the API that you're integrating with has reproducible values where you can query at a given input time or input parameter that will always yield the same result. So, if you're asking what was the price of Bitcoin yesterday on average, that's a reproducible query because the time has already passed, the data has settled, and you will always get the same response on different machines. If you're dealing with unreproducible queries, you'll get validation differences, which is something you really, really want to avoid as much as possible. There are ways to deal with this, like I described, quantizing or something else. But ideally, you're focusing on APIs that allow reproducible requests. And then ideally, as well, any external data you're dealing with should not be stored on chain directly if it's only used for validation. So, if you want to have some call, only succeed or be valid if the temperature is above 70 degrees, that information should be held in an internal data store rather than put on chain where you're just putting the same information over and over. The on-chain data really only is necessarily associated with requests and responses. It doesn't require the validation dependencies to be stored on chain because they could be reconstructed by the validators. So again, there's a lot of design choice in what data you choose to expose and put on chain, and it's best to avoid putting external dependencies on chain if the validators can internally reconstruct them. So next up, we're going to talk about permissioned or non-reproducible cases. You may have a use case that relies on a limited validator subset of Metagraph nodes that are using some sensitive information. If you have an integration with an external API that is under rate limiting, for instance, you might have IAM permissioning associated with the nodes. This means you have non-reproducible validation if you have a node that can't run that. You might have excess data volume that makes it non-reproducible. For instance, if you subscribe to a WebSocket feed at the level 2 price feed of any exchange, you're not going to have reproducible requests. It's all going to have to be captured by the validators at that time. In this case, there's essentially two situations you can do. You can either make it what I discussed with quantizing and essentially discretizing to like price averages, for instance. You can have delays in times before validation is accurate. In the WebSocket L2 example, it would take some amount of time to make sure you haven't missed any of the packets. The alternative to that is essentially distinguishing between historical versus live validation. If you want a situation where historical validation is not repeated, where it's only validated live, that's an important distinction to make upfront, early on in the design process. In the event of a WebSocket feed that's pulling price data where you're pulling, multiple gigabytes of data per day, or, tens of gigabytes of data per day, or even more, you probably cannot replicate historical validation because, first of all, those APIs are not offered for historicals without extremely huge costs. And second of all, it's too much data to process. So you need to figure out in advance whether or not your application has any of these criteria where it fits into a situation where you don't want to do historical validation. Daemon. So Marcus has talked a little bit about daemons. These are extremely useful for dealing with external services. So if you need a polling daemon, if you need to pull information from a WebSocket, if you need to grab external state information, daemons are likely the best route to go, so especially for resource constraints, because you don't want to be in a situation where you are, excessively using an API. If you're running over historical validation, you're going to be replicating all of the requests. So if you put inside a validator function an external REST API call, it could be getting reproduced every time it does some validation, as opposed to a more intelligent policy for validation where we're only pulling in the external resource once and then referencing it from within a validator function. So, again, the main uses in here for daemons are referencing external state information, user policies, Oracle information, or for bridges. We have an example that we're working on that does multi-sig operations with external bridges using a daemon in the background. And you'll find more examples of daemon in the code that Marcus referenced. So internal data stores, I've discussed this in the past, what an internal data store is. Ideally, this is an embedded database. It would simplify your deployment process a lot. If you require a custom external database, you'll need to handle and update a separate deployment script. So, if you want to use Postgres deployed somewhere, each of the validator nodes needs to be able to follow the same deployment procedure so they can each run their own separate Postgres. But other than that, the configuration is essentially the same. You can supply any sort of configuration associated with an external database or an internal database. And the key operations here you want to focus on are in the calculated state, when you're storing this sort of key value map, if it was balances, for instance, you could back this with a database that, for a given key would make a request into the database to check what the value is in the calculated state. You could update that value by updating the database. It definitely adds some complication versus an in-memory service. There's no question about that. So you do have to be careful about potential schema migrations, backwards compatibility, the correct way to handle the interconnection with validation. You want to make sure that you're not causing any locks or proper, you're doing proper thread management with the database. So it does require correct library choice and so on and so forth. But all sorts of information can be stored. Validation dependencies. If you need custom indexes that are not available on an existing Explorer, you can do this through an embedded database. If you need transforms of chain data, for instance, if you're hydrating chain data with additional information to construct user responses, you'd probably want to store that in an index. External data caches. So if you have a daemon that's pulling information, there's a large amount of it. You may want to sort of cache that internally as opposed to keeping it all in memory, putting it in a database. And then you may also want to store alternate views into the data. So this could mean, for instance, group by address and store all transactions associated with an address to store historical transaction information. That could be sort of generalized to an arbitrary state where you don't just have address as a key, but you have some other, some other transform of the data. And the last point we'll talk about is the upgrade process. So the major integration point is schema variations to the GL0, which we are trying to keep as sort of as stable as possible to make it as easy an upgrade process for you as possible. The way that we handle that is through ordinal upgrade triggers. So basically at a particular snapshot ordinal, which is the equivalent to a sort of a block ordinal, we trigger upgrades and turn on new features. So it's very important to follow the same process internally for Metagraph development, which means if you need to use new fields or add new fields to your data updates or requests or responses, use optional values, ensure the hash is stable under the changes, which it should be if you're following and using our codecs. If you're using a custom codec, you'll need to ensure the hash stability under the addition of new fields. Do not introduce these new fields until the ordinal trigger has started. It's very important. Because otherwise the nodes that are on the newer version will send data that can't be deserialized properly by nodes that haven't yet upgraded. So you want to provide some grace period so it doesn't trigger a network restart required every time there's an upgrade. And then, don't remove old fields. This is the same as this conventional schema migration problem. But it's a little more complicated because you need to make sure the hashes are stable. It's not just the values in the fields that matter, it's the hash of the overall data that matters. And this is because of the signature requires, the composition of all the fields in the data itself. In general, we've talked about a lot of different patterns here. There is one, sort of overall question of, if you don't know what to build, focus on the strengths of this framework. So focus on using custom libraries, things that are not possible with existing contract services. Client API libraries for exchanges, for weather, for IoT related data. If your idea depends on the availability of external data, it's probably a strong contender for using with Constellation. If your existing oracles don't have the data, if the latency is too low, if it's missing the right feed, if you're not able to get it, if they charge an excessive amount of money, if you want to use a machine learning library, if you want to, serve some inference model that's available on Hugging Face or somewhere else, or you want to use, H2O or any of the other JVM supported machine learning frameworks, it's perfectly appropriate to use that. That's definitely a strength. Or for whatever reason, if your application doesn't fit into a contract model, if you require additional, endpoints or peer-to-peer services or internal data storage, and you can't rely on a contract storage, then it's perfectly appropriate. And if the sort of other point is if you do not want or need an extreme number of nodes to run the validation. If you're running a microservice that requires decentralization but doesn't require a million different nodes to run it because it would be prohibitively expensive, then it's definitely appropriate. That's one of the main strengths of the Metagraph architecture.
Yes, and if you have questions and you don't have a clear idea, Constellation is providing a series of examples. We have the Metagraph examples GitHub that is also available on the documentation. And we also have two use cases of live Metagraphs that's working on right now on mainnet, the Dora Metagraph and the Alpaca one. Both Metagraphs are running for some time on mainnet. They are stable and this is open sources. So you can take a look at the code bases, see the workers that Ryle's mentioned working really in production, in handling external data, parsing data, formatting, creating, signing up data type. We have everything for you. So you can take a look and see the examples that we have.
All right. Thank you, everyone. That concludes this webinar episode.
Okay. Thanks, everyone. Bye.